In this video, I'm going to show you how to work with a ground in a circuit. This gets us single subscript voltages, which are new since I've taught you to think about voltages as always double subscript quantities measured between 2 points. Even though we're going to single subscript, we're always measuring between 2 points. It's just that 1 point is our common reference. It's the reference voltage for all other voltages. But first, let's take some measurements. I have a circuit here, 24 volts and then 18, 9, and 27 ohm resistors around it. So let's just start by taking some voltage measurements. I'll take the voltage VAB. So VAB, it's negative 8 volts. So I'm going to start sketching these on a voltage plot. So we have B being higher than A by 8 volts. So we'll just put in here node B. If you like, I'll even give it V sub B. This is our single subscript notation. All we know at this point is that it's 8 volts higher than A. So we'll put a VA there. And then let's try A to C is 4 volts, VAC. And then let's go D to C. It's negative 12, D to C, which then tells us that VCD is 12 volts. Okay, so we'll put D here, 12 volts below. All right, we have these single subscript voltages. Now, we can't really assign a value to these variables VA, B, C, and D. We simply can't because there's no intrinsic voltage for these points. But if we introduce a ground, we can define a single subscript voltage. A ground is an arbitrary node that we select in the circuit, and we're going to call it our zero voltage. So we define it to be 0. This choice is arbitrary, as I said, and it actually does not affect the circuit operation at all. So let's say we put ground on node C. So I'll show it like this in blue. And in that case, this VC, that becomes defined as our 0 volts. Then D, being 12 volts below that, takes the value negative 12 volts. A takes the value 4 volts, and then B would take the value of 12 volts. Because ground is our reference, it's really like leaving the reference here on C, and then we move the measurement point. So if I want VD, I put this on node D. You can see it's negative 12, just like I predicted in my plot there, my chart. And then if I move to A, we have a 4 volt value for VA. Keep in mind though, VA really isn't just the voltage at node A. It's the voltage between node A and the reference, which in this case is C. And then B, so VB, it's 12 volts, which is to say it's 12 volts higher than the reference. The reference is C, so it's VBC is 12 volts. And then if you look at the diagram, you can see that VBC is in fact 12 volts, and VB is 12. So I could move the ground, and I'll move it once again to D. I'm not going to erase the one at C, I'll just draw a different color. So we're moving the ground there to D. And what happens now is that D becomes our 0 volt reference. That then turns VC into 12 volts. That turns VA into 16 volts. And again, it's not like there's an actual property in the circuit that's being changed. The voltage at a single point all reference to one common place, the reference or the ground. And then finally, this is 24 volts here. Again, the choice of ground is totally arbitrary. You can pick whatever node you want, and it does not affect circuit operation. We call the ground the common reference, or the common, or the reference. I hope that helps you grasp what the ground is and what it's not. Keep in mind we're dealing with single subscript voltages here, but they're just double subscript voltages with an implicit reference of ground. I suppose for completeness, I will just measure all the green voltages where D is ground. So let's move our reference to node D. Node B is predicted to be 24 volts, and that's what we see in the measurement. Node A is the nodal voltage, 16 volts, and that's what the meter reads. C is 12 volts. Again, it's not C relative to itself, it's C relative to ground. And so we've done nice jobs predicting the different single subscript voltages based on where the ground was. Okay, I hope that helps you understand what a circuit ground is.